What's up, folks? Welcome back to the channel. In this video, we're going to talk about LangGraph, which is a framework for building agent and multi-agent workflows. It was invented by the same folks at LangChain, and it's a very interesting approach to building powerful LLM-based applications that leverage agents to solve super complex, interesting tasks. Now, first, a little bit about me. I'm Lucas. I'm an AI engineer, and I'm also curious about building tools with AI. Now, for us to understand what LangGraph is, we have to first understand what an agentic system is. Now, an agentic system is essentially a system that uses LLMs to manage the control flow of an application, right? So some of the key functions in these agentic systems are the ability to route decisions, to select tools and perform actions with those tools. A tool here means something like searching the web or checking the weather, etc. Things that a large language model by itself cannot do. And also evaluating the output sufficiency. Imagine a model has to know when it reached a point where the user request has been completed, right? Where it can solve the problem, where it can respond to the task, respond to the question. So all of that can be put into play into something called an agent loop, which is essentially, you can think about it as a little diagram that manages how an agent is going to loop over its possibilities to solve the task. And we will see an example of that to make that super clear. But essentially, it's a continuous decision-making process that enables the agent to solve complex tasks. Now, let's talk about this agent loop to give context for what is the problem that LangGraph is trying to solve. Now, essentially in an agent loop, and there are many variations of this diagram online, you have some user input that reaches some large language model. And the model makes a decision of whether to take some action, which will produce some outcome that will be fed back to the model, or to send the output directly to the user because it deems that already has enough information to respond, right? So this is a very super simple version of an agent loop that involves either calling a specific tool to execute an action or to send the output directly to the user. So that little loop that this model goes into, it's what we usually refer to when we say the agent loop. Now, why is that relevant? Imagine that we have an example of a customer support agent, right? So imagine the scenario. You have some LLM-powered customer support agent, right? The user input will be a customer asking for the order status for whatever the customer ordered. And the LLM is going to read that request, and it's going to determine if it can provide the status directly or if it needs to fetch the data from the database. In this case, probably the model needs to fetch the data from the database because that would be a sensible way to do this, because you would have thousands and thousands of requests. So it would not make sense to have all of that in the context of the large language model itself. So the model is going to make a decision to call some specific tool that fetches specific information from the database. And then the data is going to be fetched, and the agent is going to then return a response to the user, right? With the order status containing the information that was fetched from the database. So that's a very simple example of an implementation of the most simple, the simplified version of an agent loop. Okay, that's great. What are the advantages of these types of agents, and why are they so interesting? Well, they're super flexible to start, right? They can adapt to various tasks by determining the best action to take. They're super specialized. So LLM agents can be super specialized with a set of tools to perform niche tasks. Imagine you have an agent to run code, right? So the tools that agent has is like the ability to do tasks in the shell, to run Python code, etc. And then you have another one that has access to email, sending and receiving emails, sending and reading emails, and maybe, I don't know, reading files, etc. So the fact that we can specialize these agents is actually really interesting, because we've seen that if you give thousands and thousands of tools to one single agent, that agent's not going to do so well in knowing which tools to choose from in order to perform complex tasks. So finally, you have the ability to collaborate between these agents. And we've seen the surgence of a lot of frameworks right now that are trying to solve the problem of how to make these agents collaborate in order to perform really interesting and complex tasks. So LangGraph is one example, but you also have Crew AI, which is based on LangChain. You have AutoGen. You have now Llama Index has it's implementing and creating a multi-agent framework. So it's a powerful idea to have specialized agents that can collaborate to perform complex tasks. Imagine you have some task in your Jira software, right? So you have an agent that's specialized in managing your Jira tasks and then sends information about what to do to the code generation agent. And that will write some code, push it to GitHub, and then update the Jira agent that it has finished the task. And then that will also be sent to an agent that's responsible for your communication. So maybe it sends a message on Slack or sends an email to your supervisor, etc. So imagine all of these agents collaborating to perform interesting tasks. So you have these 3 points that I think make the advantages of these agents. Now, what are some of the key components of these systems? Well, you have, first of all, tool crawling, which is the ability to use external tools to perform tasks. You have action taking, which is the ability to execute actions based on LLM outputs. You have memory, which is the ability to keep track of the interactions for context-aware responses. Essentially, the ability to keep track of what happened so that the agent can then understand, okay, given that this happened, what should I do next? Or it has context on some complex task that's running for a long time. So memory is key for having powerful agents. And also planning, which is the ability to structure the steps to ensure optimal decision making. You have all of these components to make up an agentic system that's reliable, powerful, etc. Now, what's cool about LangGraph and what's cool about the recent developments of LLM-based agents is this idea of modeling everything that goes on in this process as a graph. So what do I mean? Well, we've talked about the agent loop, right? So I did this very simplified diagram here on the agent loop. And when we look at this, the insight that folks at LangChain had, and I think it's a very valid insight, and I'm excited to see what they do with this framework, is that these workflows are usually modeled and displayed and published in academic journals as graphs, right? You have some user sends a prompt to an LLM. The LLM can then choose either from an action or an output. And then if it sends the output back to the user, so these are graphs. And when we say these are graphs, we immediately think about the idea of nodes, edges, connections, exchanging of information between nodes, etc. Right? And you also have this idea of flow of information, right? Where there's some entry point, the information flows through that, right? The user input, and then all the way up to reaching some conclusion, reaching the end of a task. So LangGraph is designed for building agentic applications with some core principles based on this idea of modeling everything as a graph. So LangGraph is designed for controllability. So it offers low-level control that increases reliability in agentic systems. That sometimes can backfire a little bit, because when you work with LangGraph, you see that there are some abstractions that sometimes are not very intuitive. So you're like, why do I have to set this up? Like, how could I ever know that this was the intuitive thing to do in this particular situation? Like, I've reached that point multiple times. However, I also understand that my understanding of the abstractions needed to implement these workflows is limited. My understanding is right here. So what LangGraph is trying to do is we want to give you controllability over everything that can go on, so that you can have part of it be handled by some large language model like ChatGPT or Claude or whatever it is. But you can also have deterministic flows that perform something very specific according to what you want. And I think that this idea of trying to merge between deterministic and non-deterministic is really, really powerful. So that's why I'm giving them a little bit of I'm giving the opportunity to like really get into this framework and see what they're going to do with it, because this is super powerful. I think about it in terms of, as it's similar to like what PyTorch did when it came out, as to try to give you the ability to do something very high level, right? Just, train a model, optimize, test, and that's it. But you can also go very low at that GPU level. The other thing is the human in the loop. So you have in LangGraph this built-in persistence layer that enhances human-agent interaction patterns. There are a bunch of interesting things that you can do in terms of patterns of building these agents with LangGraph. And I think it's really cool how easy it is to put in human feedback into those loops. And that's going to be key because human feedback is going to be extremely important to curate data, right? To evaluate the outputs of intermediate parts of this flow of information that goes on inside of a graph managed by agents. So human in the loop is key. And the other thing that essentially to me initially wasn't super clear why streaming was so important, but then when I think about it in retrospect, indeed, when you're using these models, it's extremely important that you immediately see what's happening, right? And if you have to wait a few minutes to for a flow to end so that you can see everything that went on, that's not going to be great. So streaming, so LangGraph is designed for streaming first. What does that mean? That it supports streaming of events and tokens, providing real-time feedback to users. So as soon as you use it, it's going to stream out what is going on so that you have this immediate feedback. And after having used it for a while, I see now the value of, with any large language model that you use, right? You want to be able to see what happens as soon as you send an input. So the fact that it has that as one of its core principles, it's pretty interesting. Okay, that's pretty cool. But what are the components of LangGraph? Now, LangGraph models agent workflows as graphs. So as we talked about, you're going to have these ideas. They're classic when we're thinking about graphs inside of LangGraph. So nodes, edges, and conditional edges. So we're going to see what each of these are in the context of LangGraph. And nodes are going to be just Python functions that implement the logic of some agent, which will take some current state as input and will return an updated version of that state. An edge or conditional edges are going to be functions that implement some fixed or some conditional transition that determines which node to execute next based on the current state, all right? Now, I said state a few times, so let's define what states are in LangGraphs. So these graphs are going to have this initial state, which is usually something like state graph. And states are going to be shared data structures that will evolve over time as these nodes are executed and pass messages along the edges, all right? So you're going to have some sort of data structure, which is usually defined with Pydantic base model or a type dict object. And that's going to evolve over time as nodes get executed, because nodes are going to update the state and update that data structure to reach some final result. And obviously, that's kind of obvious as we talk about nodes executing functions and edges connecting nodes. You're going to have message passing between nodes. So nodes will send messages to activate other nodes, and they will facilitate the execution of workflows in discrete iterations or super steps. So essentially, you're going to pass information between these nodes, right? Now, let's do a very simple, I think the example I'm going to show you is from the actual documentation in LangGraph. We're going to start with our imports. And then from here, we're going to initialize our model. So here I have, I'm using LangChain's chat OpenAI object, which essentially gives me access to ChatGPT. I'm going to specify the model as GPT-4o-Mini, which is like a great model, super fast, cheap. It's great. Definitely advise you to use it. And now I'm going to select my kernel here. And now we're going to run this. Okay, perfect. So now I have my model. We can test the model here real quick. I can come here, I can say model.invoke, I can say hi, and then there you go, we get an answer. Now, next thing we're gonna do here is we're gonna integrate this model into, we're gonna start doing some LangGraph specific stuff, all right? And this example that I'm gonna show, I took from this page from the LangGraph docs. And the first thing we're going to do is we're going to have a function called call model, which will take in a state. And this state, in this case here, is going to be of type message state. Now, as we've talked about, state is going to be some data structure that evolves over time, right? And that data structure can be a lot of things. In this case, message state is essentially just some pre-built schema that has one attribute, which is a list of LangChain message objects. Yeah. And the logic for merging the updates from each node into the state. So this is just some pre-built object that can handle the workflow that the state is going to go through when it goes into a graph, okay? And this function, all it's gonna do is it's gonna invoke the model that we initialized there in the messages of the state, meaning the state is gonna carry all of the stuff that happened to it as it entered the graph, right? So when we invoke the model, we're saying, look, give the response to the given this context of everything that happened to the state, okay? And then we're gonna return that as a dictionary, okay? That's all we're gonna do. So we're defining our workflow, we're initializing the graph, we're gonna initialize now the state of the graph. So I'm gonna say, okay, workflow is state graph. So this initializes the graph, right? And the state that this is gonna accept is of type message state, which we already explained. Is just gonna be some schema that has one attribute and it has the logic for merging updates, etc. So this is the stuff that I mean when I say not super intuitive initially, right? However, you have to think about the fact that if you want to handle everything here as a graph, you're going to have some certain unintuitive abstractions, at least it's how I understand it, in order to be able to manage the complexity of all of these things happen within a graph. Cool thing about it is what comes next. So here we're adding a node. This is where it gets interesting. So we've talked about LangGraph as having these very important components, right? Nodes, edges, states, and message passing. So we initialize our state, right? We said workflow, state graph, and then this is going to be the type of the state. And now we created our first node, which is going to be the agent. And when we create a node, we associate the node with some function that represents what gets executed when data is sent to that node. So what's going to happen in this node is what happens in the call model function, the Python function here. So we're creating the node and we're associating it with some Python function. And this Python function does this, right? It just invokes the model that we initialized earlier in the current state messages. Since this is a super simple introduction, that's gonna be all that it is. All right, so I'm just gonna create one single silly node, and then I'm gonna set that as the entry point. What does that mean? It means when we invoke this graph, when we want to execute what's inside, it's gonna start at the agent node. So it's gonna perform the action performed within the call model function, which is this stuff here, and that's it. We're going to compile, and then we're going to invoke, and then that is it. That's all we're going to do. Okay, so when I run this, we get the output to the message, tell me a joke. Now, let's break down what's going on here, all right? This message state is some state with one attribute and has some logic for merging the updates, etc., etc. Okay, cool. In order to execute it, if I came here and I did this, let's just try to understand this complexity here. And I've just said this, hi, we get an error, right? Why we get an error? Because we did not give the correct object the input of this graph that we initialized. So it has to be a dictionary. And not only that, but it has to have the messages key, which will be a list of messages, because this is the stuff that gets updated as we move along the graph. And human message is just object in LangChain to represent an abstraction for the messages that are sent by human users, human input, etc. And then when we get that response, if we evaluate what response is, the response that we get is a dictionary containing the messages key, which will have a list of the messages sent, and then the output from the model. And we got the output like this because this is the output of calling this function here. So now that we've done this, what we can do to make things more interesting is let's forget about this stuff for a second. I'm gonna delete these. So let's make stuff a little bit more intuitive. So now that we have these, first we can do something very cool, which is to draw the graph so that you can visualize what the graph looks like after compiling. Okay, this, and instead of this, I'm gonna say app. There you go, folks. So it's kind of weird, but it is what it is. So this is what we got. So it was the super simple graph that starts somewhere, and this start is just a start node. We're not going to talk about that right now. And then that sends some output to the agent. So yeah, this is a super simplified, super basic initial graph with just one single node that performs a very simple thing. So let's go back here to these slides and let's talk about nodes. So in LangGraph, nodes are core functional units, right? They're going to be the core stuff that we work with. So the functionality, essentially, each node is going to be a Python function like we've talked about that will process the current state. Remember, state is what? Is a data structure that evolves over time as it goes through the graph, and will always output some updated version of that state, okay? So in terms of execution, nodes can run synchronously or asynchronously, and they're added to the graph using the add node method. We've seen that in this introduction simple example. So far, so good. Now, you will have some special nodes, which we did not see in this super simple initial example, but we will see in the next one, which are the start and end nodes to manage the flow of the execution in the graph, so that you have a clear start point and a clear end point. So we've already, in the introduction to LangGraph, we already talked about nodes, so let's skip this one. And now let's talk about edges. So edges in LangGraph define the routing logic. So essentially you have normal edges, which are just direct transitions from one node to another. You have conditional edges that determine the next node to execute based on the function output. And you have entry points, which specify which node to invoke first based on the user input, right? So normal edges, conditional edges, and these entry points. Now, we've seen an entry point in the introduction notebook example, where we set the entry point to the only node that we had in the graph, right? And edges also in LangGraph, they support parallel execution. So you can have multiple outgoing edges from a node that can trigger parallel execution of destination nodes. Super cool, interesting, etc. Now, let's do a quick demo on integrating edges in the context of the examples that we were talking about. So I have this little notebook here. And essentially here, I have some imports that will take care of the human messages, the calling the ChatGPT API, the adding a tool to the graph, which we'll talk about what it is and what we're doing. Memory saver, which essentially will allow us to save a specific state of our graph to memory. And then we have message state, which is that pre-built schema that has that data structure that's going to evolve, and it has just one attribute, and it has the logic to update the state as it goes. Have the state graph to initialize the state for the graph, and you have an end. This is going to be the end node, so that we know what the end of the flow is going to be. And then we're going to have something called the to node, which is a special type of node for tools that we're going to want to have the model to use. We're going to have the model using. Now we're going to define a fake search tool, which essentially will serve as a simulation for web search. I think this example I took from their documentation. So we're going to give the to decorator to this function, and then we're going to put that into a list, and then we're going to transform that into a node by giving it to the to node instance, by initializing the to node instance with this as an argument, okay? Then we're going to come here and we're going to initialize our model, GPT-4o-Mini, temperature 0, and we're going to bind that model to the tools, okay? So now this model has the ability to call this tool if it deems necessary. Perfect. And now we're going to define a function to determine whether or not to continue, given some context that's going to be implied or defined by the large language model as it processes the input coming in. So this function is where, LangGraph starts to get a little bit like, it can be a bit confusing. At least for me, it is a little bit confusing. So let's walk through it. We take in this message state. So far, so good. Some object that we can use as a state. Great. And then we're going to say, okay, the output is going to be some literal with and the end node. Okay, cool. So it's going to return end. That means end of the flow. If there are two calls, right? So if there are two calls, this is going to be, this is not going to be none, right? So when we say if not two calls, what we're doing is we're checking if there are two calls. If there are no two calls, we're going to end it. If there are two calls, we're going to return tools, and we'll see what that means, okay? Now, we're going to have that same call model function here to invoke the model on the state messages and return the same thing. We're going to initialize our state. Now we're going to add a node agent with that function call model. And then we're going to add a node tools, which will have the to node. The to node again is this to node here, right? So we have a to node, we have an agent node. And then the start point is going to be the agent. And then we're going to have a conditional edge between the agent and this function called should continue, right? So this function called should continue implements a conditional logic, okay? And the conditional logic is essentially saying, look, if there are no to calls, you end the flow. If there are to calls, you say this, okay? You return tools. Beautiful. So then we're going to create a connection between the tools, and remember, the tools here is the node called tools, and the agent. So this is actually really cool. So let's actually run this. And then we're going to initialize some memory to persist state. This is going to have, it's going to give us the ability to create checkpoints for this graph as we run through the flow. And now let's say get graph.draw. Forgot again, but get graph, draw mermaid PNG. Okay, draw mermaid PNG. And I'm going to come over here. I'm going to say from IPython.display important image. And then we're going to say image here. Now, oh, nope. Yeah, let's initialize the kernel. Function has no draw mermaid app.getGraph. Oh, sorry. So this should have been like this. There you go. So folks, we are implementing that basic agent loop that we were talking about before, right? We have a start point that flows the input to the agent. The agent can then decide to call a tool. And if it does, it will go to the to node, which implements that fake web search. And then if there are no more tools, it will send to the end. Okay, that's it. Beautiful. And now what we're doing is we're invoking that graph, right? We're initializing the graph. We already initialized it, but we're running. And we're going to invoke it. And we invoke it on this dictionary, which is going to contain a messages key, and it's going to contain a list of human messages, okay? And it's going to have some configuration for threads that we're not going to talk about. Finally, once we've run it, we can check out, and we see that when it says 9 degrees and sunny, this is exactly the output of the tool search here. So we know this model actually called the right function, the right tool. And we can inspect that by saying final state. And we see here additional keyword arguments to call. So a to call was made to that fake web search function. And then we returned an output that was returned. And we can inspect everything that happened here. This is a really cool thing. So this is the power of having this state that evolves over time, because then we can inspect everything that happened as this wonderful dictionary here, containing all the information, all the data, etc. So yeah, that's pretty cool, right? And hopefully with this, I think the most important part is to understand that when you add an edge, so here we added the main two types of edges, right? Conditional edge that should implement a function that has some conditional logic, which was this should continue function here. And a direct edge, right? Like a direct edge from tools and agent. Why? Because when you have a tool, when the tool outputs anything, that should go right back into the agent instead of sending that to something else. But we could have, if we wanted, have that tool send to something else. I mean, that could have been something we write down here. And then we compiled, we ran it. We had a check pointer with this memory saver object, which essentially will allow us to, save the state in memory. And we've visualized the graph, and beautiful, we were able to run it successfully. Now, it has a lot of stuff when you look at it, right, in terms of abstractions and things that sound a little bit complicated. But when you look at it, it's like a beautiful, very compressed, like what I like about it is that it's not about how pretty it looks in a simple example, but it's about what this makes possible in terms of complex workflows. And we're going to see a nicer example in the next notebook. So going back here, the outline of the basic agent loop in LangGraph, which we just worked through, involved setting this entry point node, right? And then we had a connection between this and the model, right? So the user input and the model. And then we had this initialized state with nodes and edges, right? So in this LLM node here that I'm talking about, in this example here is the agent node, right? And then we had this conditional edge, which was this one, that was implementing the should continue function that implements a conditional logic. And then it could have sent an output to the user, right? As we can see here in our little node, an output to the user means end here, okay? Or take an action, right? And when it takes an action, I forgot to put here actually in this diagram, but the action would send its output back to the user so that it could go back into this loop and decide if it has enough information to send to the user. I'm going to fix this diagram after this presentation. All right, beautiful. So that's the agent loop. And now let's see a more, full example. All right. So I'm going to go here. This is a basic research agent in LangGraph. Now I think this is probably not the modified version. This is an example I took from a course that I 100% recommend you check out. That is really good. And it's not anything that I've built myself. I think that the things I'm going to build in LangGraph are going to come next week, and I'm going to do some videos on it probably over the next month. But let's open up this course because this is a course I definitely recommend. I'm not sponsored or anything. I just really like courses by deeplearning.ai. I think Andrew NG does an amazing job with these courses, bringing in people that created the frameworks to actually do these courses. It's amazing. And Harrison Chase talks about LangGraph in this course. It's called AI Agents in LangGraph. I 100% recommend. I went through the entire course. It's really good. And they had an example that I really liked, which was the researcher writer agent or something like that. And we're going to walk through this example. So we're going to, if you're working with, if you don't have it as environment variables, you should have like some load.env here, and then set your environment variables for the OpenAI API key. And in this case, also for the Tavli search, I think, which is probably something we're going to use, I think, maybe, not sure. Then we're going to have some imports for handling messages, for saving the stuff to a SQLite database, and stuff for defining the graph and the state. Beautiful. So I'm going to just run this. And now we're initializing a state here. And folks, this is important. Now we're initializing a state here. It's called agent state. It's going to be inheriting from type dict. It's going to contain the task, a plan, a draft, a critique, content, revision, max revisions. So it's a state with a bunch of stuff, okay? And all of these are going to be strings, and the last two are going to be integers, okay? And now we're setting up our model, right? Just like we did before. So perfect. Now we're going to have prompts for different agents that are going to be in this graph, okay? We're going to have the planning prompt. So expert writer, task with writing high-level outline of an essay, great. Then we're going to have a writer prompt, which is an essay assistant task with writing a 5-paragraph essay, beautiful. And notice that the writer prompt takes in some content, right? Which is the information for context for the writing of the essay. Then we're going to have a reflection prompt. Reflection prompt essentially is going to, grade an essay submission. It's going to critique it and do recommendations. We're going to have a research plan prompt, which is going to search query, generate a list search queries will gather any information. Yeah. So essentially the planning stage and then the critique stage again. So you have these different prompts to manage the different behaviors of the agents involved to do the research. Here we have the base model, which essentially is going to be used to define this queries object, which we're going to use to handle making structured outputs inside of the graph, okay? And we'll see how that's done in a second. So let me just go here. Yeah. So we're just going to run this. Now, there you go. Here we have the, we're initializing Tavli that we're going to use for as our API for searching the web, okay? And there we go. We're going to run this. Beautiful. Okay, so now we're going to have a few functions to go with the prompts that we were talking about. We're going to have a plan node, a research plan node, a generation node, a reflection node, and then a research critique node. And then this should continue function. Should continue should be something that you remember from the other notebook, which will implement the logic for a conditional edge. Now, let's go through each of these functions. So in the plan node, it's going to take in a state, right? It's going to have some messages variable here with a system message. And this is the messages just for the planning stage. So we're saying here, this is the definition of a specific agent just for the planning phase. And then it's going to take in message from the human. And the message is going to be just the message under the task attribute. And then we're going to generate a response, and the name of that response is going to be plan, okay? So that's pretty cool. We're organizing how things get routed, okay? Similarly, the research plan node is going to take in the agent state, and now what's going to do is it's going to take in the queries, okay, model with structured output, and then queries. So the output of this thing is going to be the queries, okay? So we're going to invoke it on this task. And remember, if we go to this research plan prompt, you're a researcher charged with providing information that can be used when writing the following essay. Generate a list of search queries that will gather any relevant information. Only generate 3 queries max. So this prompt, it's to generate queries for some essay. That makes sense for some essay. And this is organizing the structured, fetching of those queries. And then we're looping over those queries. We're searching the web for those queries, okay? And then we're appending everything into a list and returning that. So now we generated queries for some essay, and then we looked through Tavily to search for the relevant output for those queries, and we saved all of that inside of this dictionary. Beautiful. Now, in the generation node, what we're going to do is, and you can guess what this is, right? We have the content that's going to be fetched from the state. And remember, the content's going to have all those outputs from that, searching all those queries. And then we're going to have a user message, and we're going to specify stuff inside that user message. We're going to say, look, we had this task, and then here's my plan. And then in the messages, in this messages variable here, we have a system message for the writer prompt formatted with the content from combining the task with the plan. And then we invoke it. So actually, I was wrong when I was saying that it would do that with the queries. This is actually doing with the planning. This is actually doing with the planning and the task. And then it's going to return a draft and a revision number, which I guess is going to count how many times that output, that essay was reviewed. Then we have a reflection node that's going to reflect on the draft that was generated. And then we have a research critique node that's going to essentially do the research critique, generate queries, look up those queries, and then compile all of that output and send that back. So folks, essentially what we're doing is we're creating this loop that involves the management of multiple behaviors for research, and then we're returning that. Now we're going to initialize that state graph, and now we're going to add those nodes. So that's finally the simpler part. This is what I would say is the hard part of LangGraph, because you gotta have some knowledge of the specific abstractions in LangGraph. And honestly, in my opinion, you gotta be more or less understand a little bit about LangChain, because then this would be very confusing to anyone who doesn't know LangChain, like system message, human message. These are objects from LangChain. Although LangChain is not necessary for you to run LangGraph. And then we're gonna add those nodes. We're going to set an entry point as the planner. So we're going to plan and then execute, generate, reflect, etc. We're going to add conditional edges between the generation and that function that implements the conditional logic that checks in if this number of revisions is bigger than the max number of revisions. Probably that's something going to be set by the user, right? Let me just see here. If we go up, so what is it going to be the max number of revisions? Yeah, that's sent by the user in the input. Yeah, the max number of revisions. So we have the plan, the generate, the reflect, the research plan, the research critique, and then we're going to set the entry point planner. We're going to add the conditional edges. We're going to have that conditional logic. It's going to be either end or reflect. So either you continue on that loop, reflecting and rewriting, etc., or you end it. We're going to add an edge between the planner and the research plan. We're going to compile the graph, right? So if I run this and then I run this, we can check out the graph. So it starts, we send that to the planner, send that to the research plan, and then we generate the first essay. Then we reflect on it, critique it, generate, reflect, critique, generate, reflect, critique, generate, until we reach the end. And now we can initialize that. In this case, instead of just invoke, we're streaming the output, which we can say invoke, we can say stream. We support multiple LangGraph supports. You can call invoke on the graph, but we're calling stream so that it streams out the output. So now we're in the planning phase, as you can see here. And now research plan. So it's following, as you can see here, it's following the chain, following the direction of the graph that was implemented, which is super cool, right? Now it's generating the first draft. And remember, the max number of revisions is true, so it's probably gonna generate, reflect, critique, generate, reflect, critique, generate, and then end, right? So that's what this thing is doing now. And we can wait for a second. I can skip it to the end. Okay, beautiful. We're finished. We generated a final draft after a round of generation, reflection, and critique. And that was a very simple research agent. I remember this is code taken from this course. So what I advise you to do is definitely check out this course by LangChain. Actually, the other things that I also advise you to do is check out the LangChain blog and the LangChain channel on YouTube. They have really cool stuff. One guy I really like on the channel that does amazing work is called Lance Martin. Check out his videos on the LangChain channel. They're super good. And definitely get into LangGraph. There's one very interesting blog post that I advise you to check out, which is, it's called LangGraph Multi-Agent Workflows, which was the part of the research for this video, actually. It's a really interesting article and essentially talks about agentic patterns, which we'll actually quickly cover right now. So we've talked about agent loops, this idea of managing agents together to solve complex tasks, LangGraph, modeling everything as a graph. We've talked about nodes, edges, states, this entire idea. We saw a few examples of implementation. And what's cool about this is that not necessarily when we put aside the thing with the abstractions in LangGraph, we can focus on agentic patterns. And what is an agentic pattern? Is a way to combine flows that involve, putting agents together in some specific way with certain deterministic flows in certain points in order to be able to solve interesting complex tasks. So for example, plan and execute was a very famous one, made famous by the baby AGI agent that was created in the very beginning of the agent hype, right? That involves some requests and then some planning, some generation of tasks, and then a task list that gets executed and updated until we reach a response. You also have the supervisor pattern, which essentially involves a user interacting with a supervisor that will route tasks to different agents. And you have a multi-agent workflow, which was more or less, we were doing a multi-agent workflow now. We have a user. In this case, I took this example from that blog post that I recommend you to check out, multi-agent workflows. Essentially involves managing the workloads of different agents together to get a response, managing the tools, the agents, etc. So one that's really interesting, made famous by this paper, Alpha Codem, is flow engineering, where you have this implementation of a flow to generate high quality code. So you go through a process that involves problem description, problem reflection, public test reasoning, generating solutions, ranking them, generating tests, and then you have initial solution, iteration on the tasks available, and then you iterate on the AI tests, and then you reach a final solution. So you have this flow that looks very much like a graph, right? Instead of having, asking an agent to write code for task X, right? You implement actually a process where part of the process is LLM-based, agent-based, and part of it is deterministic. So I think agentic patterns are fascinating. I think LangGraph is something worth watching out for. And that's it. Thanks for watching. Don't forget to like and subscribe, and see you next time. Cheers.